In the harsh waters of the Arabian Gulf, Dubai invested around $1 billion to build a giant sail-shaped structure taller than the Eiffel Tower. This is the Burj Al Arab, a 321-meter-tall hotel that was once the tallest hotel in the world and became known as a seven-star symbol of luxury. How did engineers anchor such a massive structure into unstable sand, resist 7,500 tons of hydrostatic pressure beneath the ocean, and suspend a restaurant 200 meters above the ground without using a single supporting column? Welcome back to Mandarin Tech. Today we will look beyond the Burj Al Arab's glamorous exterior and uncover how its engineers push the structural limits of modern construction. The Burj Al Arab stands on an artificial island off Jumeirah Beach and is connected to the mainland by a private bridge. Designed by architect Tom Wright, the building was inspired by the shape of a sail filled with wind, an image closely linked to Dubai's maritime history. Construction began in 1994, and the hotel officially opened in late 1999. It contains 202 suites, a 180-meter-high atrium, as well as restaurants, aquariums, and a helipad positioned in remarkable locations around the tower. However, the Burj Al Arab was not built only to attract tourists. It was also part of Dubai's strategy to reduce its dependence on oil and transform itself into a global destination. But before this ambitious design could become a reality, the project team first had to create the land on which the hotel would stand. But how could a hotel be built in the middle of such harsh waters? The answer was simple: create a place for it to stand by building an artificial island. First, the construction team precisely marked the outline of the island off Jumeirah Beach. Tubular piles and temporary steel sheets were driven into the seabed to define the boundary and prevent the filling material from being washed away by currents during the early stages. Along this perimeter, large rocks were transported by barges and dumped to form two protective embankments, creating a relatively enclosed area in the middle. Sand and other granular materials were then placed into the space between the rock barriers, one layer at a time. Architect Tom Wright wanted the island to remain as low as possible so that the hotel would appear to rise directly from the sea. However, the lower the island was, the easier it would be for waves to wash over its edges. The danger became clear in April 1995 when a Shamal storm produced waves between 3 and 4 meters high. A barge carrying around 10,000 tons of rock broke free from its moorings and was driven toward the shore. In response, the engineers built several scale models of the island and tested them inside a wave tank. After 3 weeks of testing, they selected the final design. The island's core was held in place by massive rock barriers, while the outer edges were shaped into sloping surfaces to reduce the direct impact of the waves. On top of these rocky slopes, workers installed hollow concrete blocks to form a continuous protective layer. When waves reached the island, the water entered the empty chambers inside the blocks, changed direction, and collided with other streams of water flowing through them. This disrupted the movement of the waves and absorbed most of their energy before it could travel deeper into the island. Thanks to this protective system, the project team did not need to build an extremely high and massive seawall. The surface of the island rises only about 7.5 meters above sea level, yet it can still withstand powerful waves from the Arabian Gulf. Once the island's surface had become stable, the construction team began excavating the basement below sea level. First, steel sheet piles approximately 20 meters long were driven deep into the island and connected to form a triangular Cofferdam. This structure supported the sides of the excavation and prevented seawater from entering from the surrounding areas. However, water could still seep through the sand from below. This could cause the ground to swell and crack, allowing the entire construction area to flood. To block the flow of water, engineers injected cement grout beneath the base of the steel walls. The grout filled the empty spaces between the sand particles and hardened into a waterproof layer below the excavation. The Cofferdam and grout barrier remained stable, creating a dry working area where the basement could be constructed below sea level. However, the basement only solved the problem of keeping seawater out. To support the tower above, the engineers still had to find a way to transfer its entire weight into ground with no solid bedrock. Survey drilling reached a depth of about 180 meters without finding bedrock. This meant the Burj Al Arab could not use piles resting on a hard rock layer. Instead, the entire structure had to stand directly on sand. The chosen solution was a system of 250 reinforced concrete friction piles. The building's weight would be transferred along the surface of each pile into the surrounding sand. The longer the pile, the greater its contact area and the stronger its holding capacity. Before construction began, sand samples were collected from different depths to test their density, deformation, and risk of liquefaction during an earthquake. The results showed that the deeper sand layers had been naturally compacted and cemented by calcium, making them stable enough to create strong friction around the piles. To provide an additional safety margin, each pile was extended by about 8 meters, more than 20% longer than the original design. The combined length of the entire pile system reached nearly 10 kilometers. As a result, the weight of the tower could be distributed through hundreds of piles driven deep into the sand, creating a foundation strong enough to support the structure above. After completing the foundations, the construction team began building the concrete core at the rear of the structure. This core contained the elevators, staircases, and utility systems. The floor slabs were then poured one level at a time and connected to 2 curved concrete wings to form the main body of the hotel. However, the tower's slender shape and the large open space in the center meant that the concrete core alone could not resist all the sideways forces acting on the building. The solution was to add a massive external steel frame, consisting of 2 large arches running along both sides of the tower and diagonal trusses connected directly to the concrete core. This system transferred forces from the exterior into the main structure and increased the overall stiffness of the building. Each diagonal truss was approximately 85 meters long and weighed nearly 165 tons. The trusses were fully welded at a factory about 15 kilometers from the construction site. They were then transported on an 80-wheel heavy-load vehicle traveling at only around 6 kilometers per hour. Police had to close the roads and temporarily remove several traffic lights to allow the enormous convoy to pass. At the construction site, ordinary cranes were not powerful enough to lift each complete section to a height of nearly 200 meters. The contractor therefore installed a specialized winching system on cantilever frames extending from the tower. Each steel truss was lifted from both ends at the same time to keep it balanced. As the structure approached its installation position, temperature differences caused the steel to expand or contract by as much as 5 centimeters. Engineers solved this problem by using washers with off-center holes before securing the connection with steel pins approximately 30 centimeters in diameter. One by one, the steel trusses were lifted, carefully aligned and locked into the 2 massive arches. Together with the concrete core, they formed a single unified structural system. However, this enormous steel frame created the next engineering challenge: wind-induced vibration. Once the steel frame was completed, the next challenge was controlling wind-induced vibration. The curved shape, large steel edges, and open spaces caused the airflow to separate as it passed around the building. At certain wind speeds, vortices formed alternately on both sides, repeatedly pushing against the steel frame. If the frequency of these forces matched the structure's natural frequency, the vibrations could gradually become stronger and threaten its stability. This phenomenon is known as vortex shedding. To evaluate the problem accurately, engineers built a 1:50 scale model of the Burj Al Arab and tested it inside a wind tunnel. Wind direction, speed, and pressure were continuously changed, while sensors measured suction forces on the façade, movement of the two steel arches, and vibration at the top of the tower. The results showed that the wind load acting on the building was almost twice that experienced by a similar building in London. In some areas, the suction force on the outer cladding was equal to the weight of a car. Changing the cross sections or rounding the edges of the steel structure could have reduced the vortices, but it would also have altered the building's sail-like shape. Instead, the engineering team installed tuned mass dampers inside the structure. Each device contained a weight of about 5 tons. When the steel frame moved in one direction, the weight moved out of phase in the opposite direction, absorbing energy and reducing the vibration. A total of 11 dampers were installed from the top mast down along the two steel arches. This allowed dangerous vibrations to be controlled without changing the building's external appearance. Once the main structural system was stable, the construction team began building the Al Muntaha restaurant at a height of approximately 200 meters. The space extends nearly 27 meters beyond the central core, with no supporting columns underneath. To support the entire structure, engineers embedded large steel anchor assemblies deep inside the concrete core. From these anchors, 10 steel beams, some measuring up to 1.6 meters in height, were extended outwards and connected to form a cantilevered floor system. Loads from the floor, equipment, glass walls, and occupants were transferred through the beams into the anchor assemblies and then distributed back into the concrete core. Once the supporting frame was completed, a lightweight aluminum and glass exterior was installed around it. Reducing the weight at the outer end of the cantilever helped limit the overturning force, while flexible connections allowed the materials to expand and contract as temperatures changed. The construction team then enclosed the open space between the tower's two wings with fiberglass fabric panels stretched between horizontal beams. Their surfaces were coated with Teflon to prevent sand and dust from building up. The tension had to be controlled precisely. If the fabric was too loose, it would vibrate strongly. If it was too tight, excessive loads would be transferred to the anchor points. High above the ground, a helipad weighing approximately 330 tons was also constructed as a cantilever more than 200 meters above sea level. Its entire load was transferred back into the main body of the tower, allowing the platform to extend outwards without any supporting columns beneath it. Together, these three elements completed the building's sail-like appearance while creating some of the most remarkable structures in the Burj Al Arab. Once the outer shell was sealed, the construction team began controlling the indoor climate. Because Dubai's air is extremely hot and humid, cooling the building too quickly could cause condensation on the structure and equipment. Inside the enormous atrium, the moisture could even form clouds and fall like rain. To prevent this, the air conditioning system lowered the temperature by less than 1 degree Celsius per day. Materials entered through a double-door airlock, preventing hot, humid air from reaching the controlled interior. The electrical load later increased by nearly 50% due to automated curtains, adjustable lighting, and electronic systems. Active filters were installed to remove electrical distortion, reduce cable overheating, and limit the risk of fire. Once the environment was stable, prefabricated marble, glass, metal, and wooden elements were installed. Lighting, fountains, aquariums, and new decorative features were also added to the atrium. After every system had been tested, the Burj Al Arab was finally ready to operate as a hotel. On February 28, 2026, the Burj Al Arab was unexpectedly drawn into a conflict that had nothing to do with tourism or architecture. During Iran's wave of retaliation following US and Israeli airstrikes, Dubai's air defense system intercepted a drone. According to the official statement, falling debris struck the hotel's outer façade and caused a minor fire, but no injuries were reported. Civil defense teams quickly brought the situation under control. The incident quickly became controversial. Dubai maintained that the damage was caused by debris from an intercepted drone rather than a direct attack. However, Images of flames on the hotel's exterior led some people to question whether the incident was more serious than initially reported. So far, there is no reliable evidence that the Burj Al Arab was deliberately selected as a separate target. The fire therefore became more than an isolated accident. The UAE viewed the Iranian attacks as a violation of its sovereignty, while for Dubai, the sight of flames on one of its greatest symbols of stability and luxury showed that regional conflict could reach even places once considered safe. The Burj Al Arab proves that bold architecture can only survive when it is supported by precise engineering. From an idea that once seemed almost impossible, the construction team transformed a sail-shaped design, on paper, into a structure capable of standing, operating, and enduring in one of the world's harshest environments. Many years after its completion, the hotel continues to capture global attention, not only because of its luxurious appearance, but also because of the engineering decisions hidden behind every curve and detail. What do you think gives the Burj Al Arab its lasting appeal? Its iconic shape, its luxurious interior, or the challenging construction journey behind it? Share your opinion in the comments, and remember to like and subscribe to Mandarin Tech as we continue exploring the megastructures transforming our world.